How can the base of logarithms be changed?
The base of logarithms can be changed from one that is not 10 or e to an equivalent logarithm with base 10 or e. The following gives the formula for such a transition, in which a, b, and x are real positive numbers, but neither a nor b are equal to 1, and x is greater than 0. Convert log x to the base b by using the formula, log(x) / log b.
What are median and mode?
The median is considered half the sum of the two numbers nearest the middle. In other words, in an ordered data set, the median is the value at the halfway point, above and below which lie an equal number of data values. But note, there is an actual middle number for a set with an odd number of members, but no middle number for an even number of members. The mode is considered a single value that occurs more often than any other in a set of data. It is not the frequency of the most numerous number, but the value of the number itself. Often there is more than one mode if two or more values are commonly found in the set, often called a multimodal population.
How do functions pertain to sets?
A function in sets pertains to a correspondence between two sets called the domain and range. Each member of the domain has exactly one member of the range. It is often called a many-to-one, or sometimes one-to-one, relation. For example, f equals 1, 2, 3, 6, 4, -2, 8, 0. 9, 6, is a function, with each set of numbers being an ordered pair. This is because it assigns each member of the set 1, 3, 4, 8, 9 exactly one value in the set 2, 6, -2, 0, 6. It never has two ordered pairs with the same x and different y values. In this case, the domain is 1, 3, 4, 8, 9, and the range is 2, 6, -2, 0, 6. To show an example that is not a function, f equals 1, 8, 4, 2, 3, 5, 1, 3. 6, 11, is not a function because it does not assign each member of the set exactly one value. It assigns x equals 1 to both y equals 8 and y equals 3, or it has two ordered pairs that have the same x values to two different y values, 1, 8, and 1, 3. For more information about functions, see algebra.
What does it mean if a series is convergent?
Convergence of a series is related to the convergence of a sequence, but don't confuse them. The convergence of the sequence of partial sums, usually written as Sn, differs greatly from the convergence of a sequence of numbers, usually written as xn. For example, the series xn, and its associated sequence of partial sums, or Sn, is convergent if and only if the sequence Sn is convergent.
How did symbols for unknowns and knowns in algebraic equations develop?
In 1591, François Vite was the first to write and solve general algebraic equations by introducing the systematic use of letters as algebraic symbols. He used vowels, a, e, I, o, u, for the unknowns and consonants. The rest of the alphabet, for the coefficients, or knowns. But it was René Descartes who introduced a new way of using letters in the alphabet in his work La Géométrie. He used the letters at the end of the alphabet, X, Y, for unknowns and the beginning of the alphabet, A, B, for knowns. In many instances, these letters are italicized. This standard is still used in algebra today.
What are prime and composite numbers?
Prime numbers are positive integers, natural numbers, that are greater than 1 and have only 1 and the prime number as divisors, factors. Another way to define a prime number is an integer greater than 1 in which its only positive divisors are 1 and itself. For example, prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. All other integers greater than 1 that are not prime are called composite numbers. There are other rules. The number 1 is unique, and is not considered a prime or composite number. And one of the basic theorems of arithmetic is that any positive integer is either a prime or the product of a unique set of prime numbers. For example, the number 12 is not a prime, but it has a unique prime calculation written as 2x 2x 3.
What is the polar form of a complex number?
The polar form of a complex number is equal to a real number expressed as an angle's cosine, and the imaginary number, I, times the same angle's sine, with the angle expressed in radians. For more about angles, sines, cosines, and polar forms, see geometry and trigonometry. This is seen in equation form as r cos 8 plus I sin 8, in which r is the radius vector, 8 is the angle, and I is the imaginary number.
What is a set?
Simply put, a set is a collection of objects or entities. These are called the elements of the set. The number of elements in a set can be large, small, finite, or infinite. The informal notation used for sets is sometimes seen as x equals y, z, with brackets used to contain the elements within the set. It is stated as, X is a set consisting of the elements y, z, and so on. But more commonly sets are seen as capital letters and elements as lowercase letters. Such as A is an element of set A.
What was the House of Wisdom?
Around 786, the fifth caliph of the Abbasid dynasty began with Caliph Harun al-Rashid, a leader who encouraged learning, including the translation of many major Greek treatises into Arabic, such as Euclid's Elements. Al-Ma'mun, 786 to 833, the next caliph, was even more interested in scholarship, creating the House of Wisdom in Baghdad, one of several scientific centers in the Islamic Empire. Here, too, Greek works such as Galen's medical writings and Ptolemy's astronomical treatises were translated. Not by language experts ignorant of mathematics, but by scientists and mathematicians such as Al-Kindi, 801 to 873. Muhammad ibn Musa al-Khwarizmi, see below, and the famous translator Hunan ibn Ishaq, 809 to 873.
What is Fisher's fundamental theorem of natural selection?
Evolutionary biologist, geneticist, and statistician Sir Ronald Aylmer Fisher, 1890 to 1962, first proposed Fisher's fundamental theorem of natural selection in 1930. A mathematical concept. It states that the rate of evolutionary change in a population is proportional to the amount of genetic diversity available. He is also often credited with creating the foundations for modern statistical science.
What are quantitative and qualitative variables as used in statistics?
Variables are values used to come to conclusions in a statistical study. There are two main categories, quantitative and qualitative variables. Quantitative variables can be divided into three types. Ordinal variables are measured with an ordinal scale, in which higher numbers represent higher values, even though the intervals between numbers are not necessarily equal. For example, on a 5-point rating scale measuring attitudes toward cutting back on air pollution, the difference between a rating of 2 and may third not be the same as the difference between a rating of 4 and 5. Interval variables are measured with an interval scale, in which one unit on the scale represents the same magnitude of the characteristic being measured across the whole range of the scale. For example, the Fahrenheit scale for temperature is an interval scale, in which equal differences on this scale represent equal differences in temperature. but a temperature of 30 degrees is not twice as warm as one of 15 degrees. The third type is the ratio scale variable. This is a scale similar to the interval scale, but with true 0 points. For example, the Kelvin temperature scale is a ratio scale because it has an absolute 0. Thus, a temperature of 300 Kelvin is twice as high as a temperature of 150 Kelvin. Qualitative variables are measured on a nominal scale, or a measurement that has assigned items to groups or categories. With these variables, there is no quantitative information and no ordering of the items is conveyed. It is qualitative rather than quantitative. Religious preference, race, and gender are all examples of nominal scales.
Who were the Egyptians?
The Egyptians rose to prominence around 3000 BCE in the area we now call Egypt. But their society was already advanced, urbanized, and expanding rapidly long before that time. Although their civilization arose about the same time that words and numbers were first written down in Mesopotamia. Archaeologists do not believe there was any sharing between the two cultures. The Egyptians already had writing and written numerals, plus. The Egyptian signs and symbols were taken exclusively from the flora and fauna of the Nile River basin. In addition, the Egyptians developed the utensils for writing signs about 1,000 years earlier.
Can there ever truly be a balance in supply and demand?
As most people know from the fluctuating prices of gas, food, and other staples, and thanks to the ever-changing variables in the mix such as war and natural disasters, there is rarely, if ever, a good balance between supply and demand.
Who was the first recorded female mathematician?
The first known female mathematician was Hypatia of Alexandria, 370 to 415. Who was probably taught by her mathematician and philosopher father, Theon of Alexandria. Around 400, she became the head of the Platonist school at Alexandria, lecturing on mathematics and philosophy. Little is known of her writings, and more legend is known of her than any true facts. It is thought that she was eventually killed by a mob.
What is an improper integral?
An integral as seen above means that the function f, x, needs to be bounded on the interval a, b, both real numbers, and the interval also must be bounded. But an improper integral is one in which the function f, x, becomes unbounded. Called a type I improper integral, or the interval a, b becomes unbounded. A equals 00 or B equals plus 00, which is called a type 2 improper integral.
What is Sangaku?
Sangaku literally, mathematical tablet, and often seen as san. Gaku is the name for a form of traditional Japanese temple geometry. From 1639 until 1854, Japan was isolated from the West. Because of this, Japan developed a kind of native mathematics that was used by samurai, merchants, and farmers. They would solve geometry problems, marking their work on delicately inscribed, colored wooden tablets that hung under the roofs of shrines and temples. In general, Sangaku problems dealt with Euclidean geometry. But they were much different from Western geometric studies. Although the majority of the Sangaku are simple to solve by Western standards, others require the use of calculus and other complex methods.
What is a number?
The term number can be defined in many ways, including a sizable collection of people or things, and even an indefinite quantity or collection. In mathematics, a number, or numeral, is usually defined as a symbolic representation of a specific quantity or place in a sequence. To most people, the most familiar numbers are 1, 2, 3, 4, 5, and so on.
What is applied mathematics?
Applied mathematics is not only concerned with using rigorous mathematical methods, but also applications of those methods. It entails a wide range of research in the worlds of biology, computer science, sociology, engineering, physical science, and many other fields, especially in the experimental sciences. In each case, applied mathematics is used by a researcher to more thoroughly understand a particular application or physical phenomena. The many uses of applied mathematics include numerical analysis, linear programming, mathematical modeling and simulation, the mathematics of engineering, mathematical biology, game theory, probability theory, mathematical statistics, financial mathematics, and even cryptography.
How is infinity treated when discussing limits?
Defining infinity is a definite part of calculus, especially when discussing limits and negative and positive infinity. Whenever the inverse of a small number is taken, a large number is generated, and vice versa. In calculus, this is written as 1/0 equals plus or minus 00, but plus or minus 00 are no ordinary numbers, because they do not obey the usual rules of arithmetic, such as 001 equals 00, 001 equals 00, 2x00 equals 00, and so on. Therefore, in calculus functions, and thus limits, infinity is treated much differently.
Who was Kurt Gödel?
For about 100 years, mathematicians such as Bertrand Russell were trying to present axioms that would define the entire field of mathematics on an axiomatic basis. Austrian-American mathematician and logician Kurt Gödel, 1906 to 1978, was the first to suggest that any formal system strong enough to include the laws of mathematics is either incomplete or inconsistent. This was called Gödel's incompleteness theorem. Thus, axioms could not define all of mathematics. Gödel also stated that the various branches of mathematics are based in part on propositions that are not provable within the system itself, although they may be proved by means of logical, metamathematical, systems external to mathematics. In other words, nothing is as simple as it seems, and, interestingly enough, Gödel's idea also implies that a computer can never be programmed to answer all mathematical questions.
What is the definition of a modern computer in today's sense of the word?
In general, and simply put, a computer is a machine that performs a series of mathematical calculations or logic operations automatically. Computer specialists often divide computers into two types. An analog computer operates on continuously varying data, a digital computer performs operations on discrete data. The majority of today's computers easily process information much faster than any human. The response, output, of a computer depends on the data input of the user, usually controlled by a computer program. A computer also can perform a large number of complex operations and can process, store, and retrieve data without human interference. There is a great deal of overlap for the word computer. In a more archaic sense, a computer is called an electronic computer, or computing machine or device. The more common expressions include data processors or information processing systems. But remember, there is a definite difference between a computer and a calculating machine. A computer is able to store a computer program that allows the machine to repeat operations and make logic decisions.
How can a calculator determine the limit of a sequence?
Here is an excellent way to understand the limit of a sequence by using a calculator. In scientific calculators that include geometric functions, such as cosine, sine, and tangent, a limit is easy to see. Find x1 equals cos 1, then x2 equals cos x1, and so on. Just put the calculator in the radian mode, enter 1, and then hit the cosine key repeatedly. The number will start at 0.5403023005, then change to 0.8575532215, and keep changing. As it approaches about the 20th change, the amount gets closer and closer to a number that begins as 0.73. This indicates the limit of the sequence is being reached.
What are the divisions found within the field of geometry?
The geometry field has several distinct divisions, including plane geometry. This includes common features such as circles, lines, triangles, and polygons. Solid geometry. This also includes such figures as circles and lines, as well as polyhedrons. Spherical geometry. This includes shapes such as spherical triangles, see below, and polygons. Analytic geometry, also called coordinate geometry. This includes the study of figures in terms of their positions, configurations, and separations. There are other types of geometry, too, including projective geometry and non-Euclidean geometry. Most of these are more complex forms of geometry that each have their own special reasons for use.
So how is the arrow's motion perceived?
Finally, one of the most interesting and insightful paradoxes is attributed to Socrates thus. It is called the Socrates paradox. It is based on Socrates' statement, "One thing I know is that I know nothing."
Can Newton's three laws be expressed mathematically?
Yes, Newton's three laws are all based on mathematical formulas. But the equations would be too complex for this text. They are defined, some with applicable mathematical notation, as follows: Newton's first law. Law of inertia, states that without any forces acting on an object, it will maintain a constant velocity. In other words, an object will stay still or keep moving in a straight line until something pushes it to change its speed or direction. The one force that stops almost everything from standing completely still or moving in a straight line is gravity. This is easily seen when you throw a baseball in the air. The ball does not move in one continuous, straight direction because the Earth's gravity pulls it downward toward the surface. Newton's second law, law of constant acceleration, states that if a force acts on an object, the object accelerates in the direction of the force. The force creates an acceleration proportional to the force, and inversely proportional to the mass. This is written in the following notation: F equals ma, in which F is the force, m is the mass, and a is the acceleration. Newton actually expressed this in terms of the calculus, a form of mathematics. he created to explain these physical laws. For more about the calculus and Newton, see History of Mathematics and Mathematical Analysis. Newton's third law, or law of conservation of momentum, states that forces on an object are always mutual. To put it another way, if a force is exerted on an object, the object reacts with an equal and opposite force on the phenomenon that initially exerted the force. Simply stated, objects exert equal but opposite forces on each other. This is often phrased, for every action, there is an equal and opposite reaction. The mathematical equations for these forces are complex and beyond the scope of this text.
What is a mathematical space?
Outer space may be the final frontier to some people. But back on Earth there are also numerous types of space in mathematics. For the most part, mathematical space consists of points, sets, or vectors. Each space and the members of that space obey certain mathematical properties. Most spaces are named after their principal investigator, including Euclidean and Minkowski space. One of the most general types of mathematical spaces is called the topological space.
What are some simple probability events?
The probability measure of an event is sometimes defined as the ratios between the number of outcomes. There are many simple illustrations of probability events, many of which we are all familiar with. One of the simplest examples of probability is tossing a coin. With a sample space of two outcomes, heads or tails. If a coin were completely symmetrical, the outcome would more likely be 0.5, ratio of 1/2, for heads and 0.5 for tails. As we all know, it never comes out that way. Which may or may not mean our coins are not in perfect balance. Another example is weather records. Many of us keep track of weather over the years. But if one were to gather all the records for the day of May 10th over 30 years from the Weather Service, one could do some simple probability event measurements. For example, take a fictitious sampling of the cloud-covered days in a certain area for the last 30 years on May 10th. Say there were 10 cloud-covered May 10s in 30 years. Thus, the probability measure would be a ratio of 10/30ths to the event that the day will be cloudy on May 10th. Insurance tables are also figured out in a similar way. For example, if, out of a certain group of 1,000 persons who were 25 years old in 1900, 150 of them lived to be 65, then the ratio 150/1,000 is assigned as the probability that a 25-year-old person will live to be 65. On the other hand, the probability of such a person not living to be 65 is 850/1,000, because the sum of the two measures must be equal to 1. It is true that such a probability statement is valid only for a set group of people. But insurance companies get around this by using a much larger population sample and constantly revising the figures as new data are obtained. Thus, even though many people question the validity of such broad-brush results, the insurance companies believe that, probability-wise, the values they use are valid for most large groups of people and under most conditions of life.
How are three-dimensional Cartesian coordinates determined?
The three-dimensional coordinates are those that describe a solid or three-dimensional object with three axes, or three planes, the usual two axes, as in the two-dimensional system, and an additional line. The coordinates are usually written in terms of x, y, and z, and are often called ordered triples or just triples.
What is chaos theory?
Chaos theory is one of the newest ideas in mathematics. Developed in the last half of the 20th century, it affects not only math, but also physics, geology, biology, meteorology, and many other fields. Modern ideas about chaos began when theorists in various scientific disciplines started to question the linear analysis used in classical applied mathematics, most of which presumes an orderly periodicity that rarely occurs in nature. In the search to discover regularities, the idea of disorder had been ignored. To overcome this problem, chaos theorists developed deterministic, nonlinear dynamic models that explain irregular, unpredictable behavior. By 1961, American meteorologist Edward Norton Lawrence, 1917, noticed that small variations in the initial values of variables in his primitive computer weather model resulted in major divergent weather patterns. His discovery of a simple mathematical system with chaotic behavior led to the new mathematics of chaos theory. The use of chaos theory has enabled scientists and mathematicians to reveal the structure in aperiodic, unpredictable dynamic systems. For example, it has been used to examine crystal growth, the expansion of pollution plumes in water and in the air, and even to determine the formation of storm clouds. One of the reasons chaos theory has come to the forefront of science and mathematics is because of advancements in computers. High-end computers allow for a plethora of variables to enter into the complex chaos equations.
What are time zones?
Time zones are any of the 24 regions on the globe, loosely divided by longitude but more erratic in their demarcations, which is divided according to the number of hours in a day. Within each zone, all clocks are set to the same time. Time zones include the International Dateline, an imaginary line of longitude generally 180 degrees east or west of the prime meridian. The date becomes 1 day earlier to the east of this line. Time zones are truly a product of mathematics. Initially, people used local solar time, resulting in slightly different times between towns. With technology, especially trains and telecommunications, more accurate timekeeping became a necessity. Thus, time zones helped solve many of the problems by setting the clocks of a region to the same mean solar time. The time zones made it easy for neighboring time zones to be labeled 1 hour apart. Not that the system is perfect. The hour separation is not universal. And because they often follow political boundaries, the shapes of the time zones can be extremely irregular.
What are some simple rules of exponents?
There are several simple rules when it comes to exponents. These include the following: the equation x1 equals x, or a number raised to the 1 power is the number itself. This is also called the rules of 1. The equation x0 equals 1, unless x equals 0, which is considered undefined. This is also called the zero rule. A number without an exponent has an exponent of 1, as in 20 equals 201. A negative exponent indicates that the number is to be divided by the exponent instead of multiplied. For example, 3 to 3 is equal to 1/33, or 1/27. But there is a restriction to this rule. Xn equals 1/xn only when x is not 0. If x is 0, then xn is undefined.
The problem with this proof?
If x equals y, then xy equals 0. Notice that halfway through the proof, the equation was divided by xy, which makes the proof erroneous.
How was the standard foot determined?
Whatever the true story, the foot we are familiar with today is equal to 12 inches, 30.48 centimeters. The true standardization of the foot came late in the 19th century. After the United States and Britain signed the Treaty of the Meter. In this treaty, the foot was officially defined in terms of the new metric standards being adopted overseas. In the United States, the Metric Act of 1866 further defined the foot as equal to exactly 1200/3937 meter, or about 30.48006096 centimeters. This unit of measurement is still used for geodetic surveying purposes in the United States, and is called the survey foot. By 1959, the United States National Bureau of Standards redefined the foot to equal exactly 30.48 centimeters, or about 0.9999998 survey feet. This definition was also adopted in Britain by the Weights and Measures Act of 1963, thus, a foot, or 30.48 centimeters, is also called an international foot.
Were there any problems with the Babylonian numbering system?
Yes. One in particular was the use of numbers that looked essentially the same. The Babylonians conquered this problem by making sure the character spacing was different for these numbers. This ended the confusion. But only as long as the scribes writing the characters bothered to leave the spaces. Another problem with the early Babylonian numbering system was not having a number to represent 0. The concept of 0 in a numbering system did not exist at that time. And with their sophistication, it is strange that the early Babylonians never invented a symbol like 0 to put into the empty positions in their numbering system. The lack of this important placeholder no doubt hampered early Babylonian astronomers and mathematicians from working out certain calculations.
What is a field?
A field is an algebraic structure that shares the common rules for operations. Addition, subtraction, multiplication, and division, except division by 0. Of the rational, real, and complex numbers, but not integers, see below under ring. A field must have two operations, must have at least two elements, and must be commutative, distributive, and associative, see above for definitions. Formerly called rational domain, a field in both French corps, and German, Körper, appropriately means body. A field with a finite number of members is called a Galois or finite field. Fields are useful to define such concepts as vectors and matrices.
What techniques are used to solve first-order differential equations?
There are usually three major ways to solve first-order differential equations: analytically, qualitatively, and numerically. The analytical way includes the examples mentioned above, such as the linear and separable equations. Qualitative methods include such methods as defining the slope of a field of a differential equation. Finally, numerical techniques can be thought of as something close to Euler's method, a way of finding the largest divisor of two numbers.
What are first-order homogeneous and non-homogeneous linear differential equations?
These differential equations may be long-winded phrases, but they are actually types of first-order differential equations. A first-order homogeneous linear differential equation can be written in the notation as follows. T plus a, t, y, t, equals 0. The first-order homogeneous linear differential equations are those that place all terms that include the unknown equation and its derivative on the left-hand side of the equation. On the right-hand side, it is set equal to 0 for all t. The non-homogeneous linear differential equations are those that, after isolating the linear terms containing y, t, and the partial differentials inside the above large parentheses on the left side of the equation, do not set the right-hand side identically to 0. It is often represented by one function, such as the b, t, see below. The standard notation is as follows: ty, t, plus a, t, y, t, equals b, t, usually in reference to time. Such problems are called initial value problems. The other condition is the boundary condition, in which constraints are specified this time at the boundary points, usually in reference to space, with such problems called boundary value problems.
What are dice?
Dice are small cubes usually used in games of chance. Each dice is the plural, has 6 sides numbered with dots from 1 to 6. The dots are placed on the cube so that the sum of dots on opposite sides equals 7. The total number of dots on each die equals 21. They are mostly associated with certain types of games, with the simplest involving a player, or many players, who throw, or toss or roll, the dice for the highest sum. Dice have been around for more than 3,000 years, with evidence found in ancient Egyptian tombs, Chinese burial chambers, and the ruins of Babylon. The Greeks and Romans were avid users of dice and associated games, and they have been popular from the Middle Ages on. Dice have been made from many materials, including ivory, bone, wood, metal, and eventually plastic. Not all dice are square. The cube, or hexahedron, belongs to the group of 5 Platonic solids, or solids formed by regular polygons. Thus, other Platonic solids have also been made into dice, including shapes, polyhedra, such as tetrahedrons, octahedrons, and dodecahedrons, which are used for certain types of games. For more information about Platonic solids and polyhedra, see geometry and trigonometry.
When was quantum mechanics developed?
There was not one major year in which quantum mechanics was developed, or even one major scientist who proposed the idea. This modern theory of physics evolved over about 30 years, with many scientists contributing to it. Beginning about 1900, Max Planck proposed that energies of any harmonic oscillator, such as the atoms of a black body radiator, are restricted to certain values. Mathematics came into play here, too, with each value an integral multiple of a basic, minimum value. Planck developed the equation E equals hv, or h times nu, in which E, the energy of the basic quantum, is directly proportional to the v, the frequency of the oscillator, multiplied by h, or Planck's constant, 6.63 x 10 to 34 joule-second. From there, mainly with the use of rigorous mathematics, others expanded or added to Planck's idea, including German scientist Albert Einstein, 1879 to 1955, who explained the photoelectric effect. New Zealand-born British physicist Ernest Rutherford, 1871 to 1937, and Danish physicist Niels Bohr, 1885 to 1962, who explained both atomic structure and spectra. Austrian physicist Erwin Schrödinger, 1887 to 1961, who developed wave mechanics, and German physicist Werner Karl Heisenberg, 1901 to 1976, who discovered the uncertainty principle. Out of these studies came quantum mechanics, in the 1920s, quantum statistics, and quantum field theory. Today, quantum mechanics and Einstein's theory of relativity form the foundation of modern physics. These theories continually change or are modified as we get closer to understanding more about the physics and mathematics of our universe.
How are some common solids defined?
There are numerous objects defined in solid geometry. The following lists the most common, and some interesting ones. Cone. A cone can be both a surface and a solid. A solid cone is bounded by a region enclosed in a closed curve on a plane and a surface, formed by segments joining each point of the closed curve to a point that is not in the plane. Note, two solid cones seen with their pointed ends together help define conic sections. For more about conic sections, see elsewhere in this chapter. Pyramid. A pyramid is a polyhedron, see above, with one face a polygon and all other faces as triangles with a common endpoint, vertex. They are named based on the polygon's base, such as the triangular pyramid, square pyramid, and so on. Some of the most famous solid pyramids are the sandstone pyramids of Egypt. These are actually called right square pyramids because the base of the polygon is a square and the vertical line from the vertex meets the center of the base. Cylinder. A cylinder can be both a surface and a solid. A solid cylinder is one that forms by rotating a circle about an axis through the midpoints of the opposite side. It is also called a right circular cylinder. One of the most well-known cylinders is possibly sitting right next to you, a coffee cup. With its cylindrical shape, and the bases, in this case, the base and rim, considered to be congruent circles. Prism. A prism is a polyhedron with two parallel, congruent faces that make up the bases of the shape. The other, lateral faces are considered to be parallelograms. If the lateral faces are rectangles, the prism is called a right prism. Parallelepiped. This strange-sounding polyhedron is one that has all its faces as parallelograms, or a prism with parallelogram bases. The most familiar parallelepiped is a simple box, also called a rectangular parallelepiped that has rectangles for all the 6 faces. For more about these figures, including how to calculate their areas, see elsewhere in this chapter.
What did Blaise Pascal invent that eventually caused his interest in math to wane?
French mathematician and philosopher Blaise Pascal. 1623 to 1662, devised the Pascaline in 1642, when he was only 18 years old. He had it built by 1643. This device was possibly the first mechanical adding machine used for a practical purpose. He built it with his father, a tax collector, in mind to help him with the tedious task of adding and subtracting large sequences of numbers. But the device was not very helpful for a variety of reasons, especially since it used base 10 and did not match up with divisions of the French currency. Other reasons for its rejection are familiar to every century. The device was much too expensive and unreliable, along with being too difficult to use and manufacture. Eventually, Pascal's interest in science and mathematics waned. In 1655 he entered a Jansenist convent, studying philosophy until his death.
What are some divisions of polygons?
There are 2 major divisions of polygons. Regular polygons are convex polygons with equal sides and length. Thus, all sides and angles are congruent, equal. For example, one of the most famous regular octagons is the stop sign used along roads in the United States. A closed polygon with 8 equal sides. The naming of the various polygons can be challenging, though. For example, a polygon called a regular triangle is also called an equilateral triangle. Another name for the polygon called a regular quadrilateral is a square. Irregular polygons are those with sides of differing lengths and variable angles. Therefore, unless all the sides of the polygon are of the same length and all the angles are of the same measure, the polygon is said to be irregular. But don't be fooled, the names for the various polygons such as hexagon, nonagon, and pentagon, depending on number of sides, don't just apply to the regular polygons, but rather to any two-dimensional closed figure with the number of sides as described by its name. For example, the 2 figures shown above are both pentagons. A is a regular hexagon and B is an irregular hexagon. Polygons are described in other ways, too. Convex polygons are those in which every line drawn between any 2 points inside the polygon lie entirely within the figure. Opposite from the convex polygons are the concave polygons, those that are essentially caved in, with some of the sides bent inward. If a line is drawn between 2 points inside a concave polygon, the line often passes outside the figure. Another type of polygon is a star polygon, in which a star figure is drawn based on equidistant points connected on a circle.
When is a set a superset?
A superset is one that contains all the elements of a smaller set. For example, if B is a subset of A, then A is a superset of B. In other words, A is a superset of set B if every element in B is in A. Like a proper subset, there are also proper supersets, or a superset that is not the entire set.
What is the air quality index?
Mathematics plays an important part in the air quality index, AQI, a scale developed by the U.S. government to measure how much pollution is in the air. The AQI measures 5 specific pollutants: ozone, particulate matter, carbon monoxide, sulfur dioxide, and nitrogen dioxide. The levels range from 0, good air quality, to 500, hazardous air quality. The higher the index, the higher the level of pollutants and the greater the likelihood of detrimental health effects.
What new ideas came out of Einstein's, and others, study of relativity?
He showed that space and time could no longer be viewed as separate, independent entities, forming a four-dimensional continuum called spacetime, also written as spacetime. It is not easy to verbally explain the intricacies of Einstein's theory. The best way to interpret his works is with the use of formulations from certain mathematical branches, such as tensor calculus. For more about tensors, see mathematical analysis. But such complex equations are beyond the scope of this book.
What are functions?
Functions are mathematical expressions describing the relationship between variables and involve only algebraic operations. If there is one independent variable, the dependent variable, for example y, can be determined through the function. This is often seen written as y equals f, x, spoken as y equals f of x. Functions also use notation with x. For example, f, x, equals 2x plus 1 is a function. Functions within equations are also common. For example, in the equation x2 plus y equals 3, the y represents a function of x. This equation can also be written as y equals 3 plus x2. Functions do not always have to be in terms of f, x. They can just as easily be termed g, x, depending on the equation. But note, the equation x2 plus y2 equals 9 is not a function, as x and y are both independent variables.
When was the equal sign introduced into mathematics?
He equals sign, smiley face, is a relatively new invention in mathematics. It was first used by British mathematician Robert Record, 1510 to 1558, also seen erroneously as record. In his book The Whetstone of Wit, 1557, the first algebra book introduced in England. In it he justifies using two parallel line segments because no two things can be more equally. Sick, because no two things can be more equal than parallel lines. It was not an immediately popular symbol, though, with mathematicians continuing to use a range of symbols for equal, including the two parallel lines. Used by Wilhelm Xylander in 1575, and AE or OE, both from the word equalis, the Latin for equal. But for the most part, the word equal was written in an equation until around 1600. When Record's symbol became more readily accepted, and it continues to be so today.
How do various disciplines use applied mathematics?
Depending on the discipline, researchers use applied mathematics in various ways. For example, some disciplines rely heavily on pure mathematics. Numerical analysis, a form of applied mathematics, is a field that uses pure mathematics to decipher partial differential equations and variational methods. For more information about numerical analysis, see below. For partial differential equations, see mathematical analysis. There are also areas of applied mathematics that overlap other fields of study. For example, there are mathematicians who use applied mathematics to study the structure of matter, especially the behavior of subatomic particles, a field that also overlaps the same types of studies done by subatomic physicists.
What mathematical concept is used to calculate mortgage payments?
In most cases, a mortgage is based on amortization, which is the gradual elimination of a liability. A financial obligation or debt, such as a mortgage, in regular, fixed, systematic payments, such as monthly, over a specific period of time. These payments must be enough to cover both the principal borrowed and the interest. Although it is usually written in a complex set of mathematical calculations, simply put, amortization means a part of the payment goes toward the interest cost and the remainder goes toward the principal, or the amount borrowed. The interest is then recomputed on the amount owed. and therefore it gets smaller and smaller as the ending balance of the loan becomes less and less. That is why the homeowner pays a great deal toward interest and not the principal for the first several years of a home mortgage. For example, if a mortgage is taken out for $100,000 at 6.5% for 30 years, the fixed monthly principal and interest payment is $632.07 for the first month. The homeowner pays interest on the $100,000, or $541.67, with the remainder of the payment, $90.40, going toward principal. In other words, the debt on the principal is reduced by $90.40. By the next month, the homeowner owes interest on a lesser amount of money on $99,909.60, or $100,000 $90.40. Not the $100,000 with $541.18 going toward interest and $90.89 going toward principal. As payments are made month after month, the interest decreases and the principal reduction increases. By the 360th payment, or 30 years later, the payment contributes $3.41 to interest and $628.66 to principal.
How is mathematics used by search engines on the World Wide Web? www.
A search engine is a program that searches for internet documents, usually on the World Wide Web, using certain keywords. It then returns a list of results in which those keywords are found. Search engines such as Google, AltaVista, and Excite are a general class of programs that use a proprietary search algorithm. They rely on probability, linear algebra, and graph theory to create a list that, ideally, produces the most relevant website results for the user.
How is temperature measured?
Temperature is measured using a thermometer, thermo meaning heat and meter meaning to measure. The inventor of the thermometer was probably Galileo Galilei, 1564 to 1642. Who used a device called the thermoscope to measure hot and cold. Temperatures are determined using various scales, the most popular being Celsius, Fahrenheit, and Kelvin. Invented by Swedish astronomer, mathematician, and physicist Anders Celsius. 1701 to 1744, in 1742, Celsius used to be called the centigrade scale. It can be capitalized or not. Centigrade means divided into 100 degrees. He used 0 degrees Celsius to mark the freezing point of water. The point where water boils was marked as 100 degrees Celsius. Because of its ease of use, mainly because it is based on an even 100 degrees. It is the scale most used by scientists. It is also the scale most associated with the metric system. Fahrenheit is the scale invented by Polish-born German physicist Daniel Gabriel Fahrenheit. 1686 to 1736, in 1724. His thermometer contained mercury in a long, thin tube, which responded to changes in temperatures. He arbitrarily decided that the difference between water freezing and boiling 32 degrees Fahrenheit and 212 degrees Fahrenheit, respectively would be 180 degrees. The Kelvin scale was invented in 1848 by Lord Kelvin, 1824 to 1907. Who was also known as Sir William Thomson, Baron Kelvin of Largs. His scale starts at 0 degrees Kelvin, a point that is also known as absolute zero. The temperature at which all molecular activity ceases and the coldest temperature possible. His idea was that there was no limit to how hot things can get, but there was a limit to how cold. Kelvin's absolute zero is equal to minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. So far, scientists believe nothing in the universe can get that cold.